In our third and final video, as we discuss the IRAT for section 10.1 on sequences, we'll identify the solutions for and further discussion of questions 4 and 5. Question 4 asked about a sequence where the terms are defined as a finite sum, k going from 0 to n of 1, n, the fact that n is greater than or equal to 0, tells us which n values we're working with. And so in reality, we are adding n plus 1 ones in this sum. So we're asked to identify which choice best answers this question. So let's first, before we actually address this question, let's write out some of the terms of this sequence. So a sub 0, we are told, is the sum k going from 0 and stopping at 0 and summing 1. That means we have the term 1, because that is the term that we get when k is equal to 0. That means that a sub 0 is simply 1. A sub 1, when n is equal to 1, so here n is equal to 0, n is equal to 1, that means we have the sum k going from 0 to 1 of 1. That means when k is 0, we have the add end of 1. When k is equal to 1, we also have another 1. So that means a sub 1 is actually 2. If n is 3, the third term of the sequence, n is 2, the third term of the sequence, so a sub 2 is equal to k, the sum, k going from 0, stopping at 2 of 1. When k is 0, we have an add-end of 1. When k is 1, we have an add-end of 1. And when k is 2, we have an add-end of 1. So that means that a sub 2 is actually 3. And we can continue on. So that a sub n, we know, is the sum k going from 0 to n of 1. And that's 1 plus 1 plus 1. Again, this is the add end we get of 1 happens when k is 0. We get another one when k is 1. We get another one when k is 2. And then when k is n. And we know that when k is 1 up through n, we have n ones that we're adding. And then we have one more when k is 0. So that means that a sub n is actually n plus 1. So that's another way of writing the sequence. So I could say that this sequence, a sub n, and starting at 0 and continuing to infinity, is also the sequence of n plus 1 and going from 0 to infinity. Is this a sequence? Well, it most certainly is. So we can cut off choice A. Let's address these other questions. Is the sequence convergent or divergent? Again, a sub n being the sum k going from 0 to n of 1, which we know is n plus 1. This sequence, when we consider the limit of the terms as n goes to infinity, is going to be the limit of n plus 1 as n goes to infinity, which we well know has a limit of infinity. So we say that the series diverges. Okay, so we can eliminate choice B and choice C. Okay, let's check. Is the sequence increasing, and do we know if it is bounded or not? Well, we obviously know that the sequence is in fact increasing because as n increases, we're adding 1, and so we can say that a sub n plus 1 in comparison to a sub n. A sub n plus 1 is certainly bigger than a sub n because we know that n plus 1 would be the n plus first term, which is certainly bigger than n plus 1. So therefore, we know that the sequence increases. And we also know that the sequence is not bounded because it's not bounded above. Because if I specify any m, I can simply just choose a sub m, because that's going to be a sub m plus 1, which is going to be bigger than m. So for any large value that I would choose, I'm always going to find a term, namely a sub m, that's bigger than that number that we specify. So the correct answer to question 4 would be choice C, because it is, not bounded. Not bounded. So a sub n is increasing, not bounded above, and in fact diverges. Now, this question actually is a great lead-in to what we'll discuss in the next section. And in this next section, section 10.2, we're going to begin discussion of series. And in series, we are going to simply take a sequence. We'll say the sequence of a sub k, k going from 1 to infinity, which is a sub 1, a sub 2, a sub 3, and so on. We'll let this be a sequence. We'll say it's a sequence of terms. Okay. We're going to form a new sequence. Okay. And we're going to call this sequence a sequence of partial sums. Okay? And the way that we're going to do this is we're going to say S sub 1 is simply the first term, a sub 1. S sub 2 will be I'm going to take a sub 1 and add a sub 2. S sub 3 will be a sub 1 plus a sub 2 plus a sub 3. And that pattern will continue so that the nth partial sum, denoted S sub n, will be a sub 1 plus a sub 2 plus a sub 3, and we'll keep adding the terms of the sequence that we have. And then we can use some shorthand notation by saying it's the sum, k going from 1, stopping at n, of a sub k. If we look at the limit of this new sequence, so the limit of S sub n as n goes to infinity, if this sequence converges, which we'll write as script s, so in other words, the limit of the sequence of partial sums if that limit exists, then we write that the series k going from 1 to infinity of a sub k equals that limit of the sequence of partial sums. And so then we call this an infinite series. Okay. So we have multiple things going on here. We've got a sequence of terms, a sub 1, a sub 2, a sub 3, and so on. Then we develop a new sequence. We call this a sequence of partial sums, where S sub 1 is a sub 1, S sub 2 is the sum of the first two terms, and so on. We also have a sequence here of S sub n's. And we can look at multiple limits. We can look at the limit of the sequence, but now we also look at the limit of the sequence of partial sums. And that will help identify if the infinite series converges or diverges. So that's, again, a preview of the next section. We'll finish out this video by talking about problem 5 of the IRAT. And in question 5, we have the limit as n goes to infinity of 1 minus 1 over 2n raised to the n power. Does this limit exist? And if so, what is that limit? Okay. From the book on page 584, you had a list of important limits. Now you can either memorize these limits or you can make sense of them and derive them. But this is one of the limits, specifically if we consider the limit as n goes to infinity of 1 plus x over n raised to the nth power. We are told that this limit is equal to e to the x, and we can justify this. And so if we take the limit that we have, the limit as n goes to infinity of 1 minus 1 over 2n raised to the nth power, I can rewrite this limit. The limit as n goes to infinity of 1 plus a negative 1/2 over n. And we now have it in that same form, and so this is going to be e to the negative 1/2, or 1 over e to the 1/2 power, or 1 over the square root of e, which is choice B. So that's one way to solve this problem. I am not a big fan of memorizing formulas, so I like to use the brute force method and figure out the limit. So let's look at this limit another way. So first of all, if I take a look at the limit as n goes to infinity of 1 minus 1 over 2n raised to the nth power, as n gets really, really large, 1 over 2 to the n is going to get very, very small and close to 0. So this looks like 1 to a very large number. Now this is not 1, this is an indeterminate form. So therefore, we can apply L'Hopital's rule once we get it in a form where we have a function divided by another function. So let's go ahead and say we think this limit exists. Well, we know this limit exists, but let's go ahead and say this limit equals L. Because I've got an exponent that is a variable, I'm going to take the natural log of both sides. And because the natural log is a continuous function, when when our input is positive, I can use the properties of limits and say I've got the limit as n goes to infinity of the natural log of 1 minus 1 over 2n raised to the n power. Properties of logarithms allow me to bring that n down. Furthermore, I can multiply by a form of 1 in order to get that function over a function. So I'm going to have the limit as n goes to infinity of the natural log of 1 minus 1 over 2n divided by 1 over n. And now as I let n go to infinity, I've got the natural log of 1 over 1 over a large number, so this is a 0 over 0 form. So now I can apply L'Hopital's rule, and I get the limit as n goes to infinity of 1 over 1 minus 1 over 2n times a negative 1/2 times a negative 1 over n squared, all over a negative 1 over n squared. So this will cancel with this. As n gets really, really large, I get a negative 1/2, but that is the natural log of the limit that I need, so therefore the natural log of L is negative 1/2, so L is equal to e to the negative 1/2. And I get an answer of B again. If we consider the graph of the situation, again, where the inputs are the positive integers, so n equals 1, 2, 3, 1, 2, 3, 4, 5, and so on. These are the terms of that sequence. Again, if I'm taking the sequence to be 1 minus 1 over 2n, all raised to the nth power. And there's a graph. Again, the fact that this limit exists suggests that we have a horizontal asymptote. And that concludes our discussion of the IRAT for section 10.1.